So, today we will be continuing our discussions on the measurement of two-phase flow parameters. In the last class, I had discussed the measurement of the most basic flow parameter, I should say, the pressure drop measurement, which you have been doing very frequently, I think even in your undergraduate fluid flow laboratories and things like that, isn't it? So, there also we found that definitely it is not impossible, but special care has to be taken when one goes for the measurement of two-phase pressure drop or pressure drop when two-phase flow occurs through any particular conduit. Okay. Today we are going to start our discussions on the measurement of one of the most vital parameters of two-phase flow, that is how to measure its in situ composition. Since we are mostly dealing with gas liquid flows because maximum number of literature are available. So, we will be mentioning it in terms of measurement of void fraction, but even if it is liquid systems or any other two-phase systems or three-phase systems, it is just the measurement of the in situ composition of the two phases. Why it is so very important? It is so very important because the first thing is the in situ composition is not related to the inlet composition in a straightforward manner. It depends upon a large number of factors which are a function of the distribution of the two phases, the flow rates of the two phases, the physical properties, the conduit dimension, conduit orientation, and so on and so forth. Now, if there is no direct relationship between the inlet and the in situ compositions, then we can measure the inlet composition, but we cannot determine the in situ composition in a straightforward manner. Okay, and this particular in situ composition, that is very important for prediction of any hydrodynamic parameters of two-phase flow, or for that matter for any particular further studies on two-phase flow. Unless we know the distribution of the voids, unless we know the void fraction, we cannot proceed further for any further analysis. Okay, so therefore, I thought that it's prudent to spend good amount of time on void fraction. We will be probably doing 1.5 or 2 classes on this, and then finally, I will be ending up this course with the estimation of flow patterns. Okay. Now, what are the importance of void fraction measurements? Now, more or less as I have said that the void fraction gives us a measure of the in situ composition of the two phases. So, therefore, unless we can measure the void fraction, we do not know the composition. Unless we do not know the composition, we do not know the mixture density, the in situ velocity, etc., etc. So, therefore, the first thing in industrial situations is to calculate the pressure gradient or the pressure drop. If we have to calculate the pressure gradient or the pressure drop, as you already know that for the gravitational pressure drop is the most important pressure drop component for vertical systems, that cannot be evaluated without a knowledge of alpha or liquid hold up HL. The next thing is it calculates the liquid and gas inventory which is present in the system. Okay. And so, therefore, suppose you have to calculate what amount of material is needed within a chemical plant. So, therefore, for such particular applications, liquid hold up, an estimation of liquid hold up or an estimation of void fraction is very essential. And then of course, some special applications, there is no point in discussing applications of void fraction measurements, you already know it, but these are just some of the salient applications. In nuclear reactor absorption and moderation of neutrons related to density of vapor liquid mixtures, this also it is related to void fraction. So, therefore, as the last application is just to show as we progress more and more and come across newer applications of two-phase flow, the importance of void fraction is further augmented. Now, so what are the different techniques of measurement of void fraction? We have already discussed that void fraction or the in situ composition is nothing but more or less the fraction of the total channel which is occupied by a particular phase. Fraction of the total channel obviously means the fraction of its total volume, or it obviously means the volume fraction void fraction or the volume fraction liquid hold up. But as we had already discussed, in order to see, suppose you have to measure the volume fraction, so the entire volume has to come into your control. Several times it happens that it's not always possible to measure the volume fraction void fraction. So, therefore, then we go for an area average value as I have shown here. Okay. And under steady state conditions, for fully developed flow, we can assume that area average gives a reasonable estimate of the volume average void fraction as well. There can be circumstances where neither the volume average nor the area average is possible. Under that circumstance, what we do? We go for the caudal average void fraction, which gives us the void fraction across say the diameter of the channel cross section or across any particular chord. Okay, I have shown it here, you can see it. This gives you the volume average. If we concentrate on a particular cross section, then this entire thing gives us the area average. I have already discussed these things. Here for example, suppose we concentrate on a very thin section, very thin segment, it gives us the caudal average. Now, there are certain times where we would like to have a idea of the point average, if you say, or the void fraction at a point. As I have already mentioned long back during our introductory lecture, that the point average void fraction has got no meaning, because the void fraction at a point will either be 1 or 0. So, in this particular case, what is relevant? The variation of void fraction at that particular point, or if we measure the void fraction at the point over a good length of time, then in that case void fraction or during void fraction of the time, that particular point was occupied by the gas phase, void fraction of the time that point was occupied by the liquid phase, or in other words this gives you the time average void fraction. There is nothing like the point average void fraction. This is particularly important. Why? Because from all these above quantities, we had obtained the averaged void fraction over some particular section of the channel. It can be over a volume element, an area element across a chord, but it gives over that particular element, it gives the average void fraction. But this thing, it actually gives us the distribution. It is sometimes very important to know the distribution also rather than the average values, because once you know the distribution, say for example, you want to perform a chemical reaction, a gas liquid or liquid whatever a reaction. Naturally, the rate of reaction will depend upon the distribution, how they are distributed. In some places, if they are sparsely distributed, the reaction will take place at a lower rate. Where there is a larger concentration of reactants, the reaction will take place at a faster rate. Okay, so, we would always like to ensure that they are more or less uniformly distributed, or else we would like to predict the rate of reaction by knowing the distribution. Unless we know it, just if we assume some average value, then we might not get correct results. So, it is very often very important to know the profile rather than the average value. In order to find out the profile, the time average void fraction is very important. Okay. So, there are different techniques of measuring the volume average the void fraction measurements. They can broadly be categorized into volume measurement. Simply by some process, you very directly you measure the volume which is occupied by phase 1, volume which is occupied by phase 2. Naturally, this is the most direct method and this is the most standard method. Definitely, there are some problems in using it in industries, due to which other measurements have come up, but remember one thing, everything has to be calibrated with this volume measurement value before they can be used for further applications, right. So, therefore, the one thing is direct volume measurement. Okay. Now, remember one thing, whenever we are trying to measure void fraction, we have to keep in mind certain things. See, we have to exploit some particular physical property which is different for the two phases. Do you agree with me? Only that particular physical property will have a particular value in say the gas phase, a different value in the liquid phase, something intermediate when it is a two phase mixture. If we have that, if we can identify such a type of physical property, and it is not very difficult to estimate or measure that particular physical property, and more or less its response is quite fast, it is not very expensive, we can adopt it for void fraction measurement, correct. Some property has to be there which is widely different for the two phases. Now, what can it be? First thing is density, it is definitely going to be different for the two phases. So, based on density, the two phases can separate out and we can measure the fraction. The other thing, suppose it is not so very easy, the volume measurement I will tell you. The most direct way of doing it is very evident to you. A two phase mixture is going, there are two valves attached at the two ends or across a particular section of the entire test rigs. They are closed simultaneously. This it is a very common technique. They are closed simultaneously to arrest the two phase mixture within them. Now, once they are arrested, naturally due to difference in density they will separate out. It is very easy to measure the void fraction or the liquid hold up from this particular measurement. Very easy, very accurate, and in fact all methods are based on this particular technique. But if it was so very easy, so very friendly everything, then there was no need of devising any other method. It must be having some disadvantages. Despite so many advantages, when we are not adopting it as a sole method, definitely there are some problems with it. What are the problems of this particular technique, which is known as the quick closing valve technique? Remember certain things, there has to be valves at the top and bottom. Important thing is they have more or less, they should not be obstructing the flow when they are fully open. If they obstruct the flow when they are fully open, then definitely they are going to influence the flow distribution here, the void fraction here, and in that case we will not get an accurate measurement. First thing, their inside bore should be equal to the diameter of the tube, so that they do not obstruct the flow. What is the second thing? Both of them have to be closed very fast and simultaneously, instantaneously and simultaneously, so that at one particular instant both of them are closed and the mixture gets arrested. If we take a finite time to close, then during that time the flow distribution will be changing, because during that particular finite time naturally this it is going to obstruct the flow passage and the flow distribution is going to change. So, definitely we cannot use a gate valve for this particular purpose. Okay. Normally the thing which is done is we can use two ball valves or maybe electrically operated solenoid valves, which is the best, because in that case maybe one or two particular switching off is going to stop the flow there. Okay. The other thing is, suppose you use mechanical valves, then in that case they have to be linked up by some particular mechanical linkages, so that they can be closed simultaneously. Okay. So, these things have to be kept in mind. So, in short, what are the problems of the quick closing valve technique? First thing is, it takes a finite time to close the valves, and during valve closure time flow pattern might change within the channel. Okay. So, in practice it has been observed that void fraction is more or less insensitive to the closure time if the valve closing is relatively brisk and there is a proper synchronization between the valves, or both of them can be closed simultaneously. But the most important disadvantage I did not tell you. See, when you are practicing, then what you are doing? You are actually stopping the flow. You are closing the valves, you are actually stopping the flow. Okay. Now, thing is, you have to keep two things in mind. This flow then has to be diverted through some other portion, otherwise it will accumulate and it will create a large amount of transient pressure, maybe the blow down of this test section. So, this firstly has to be kept in mind. The other thing is, or else you can simply stop the flow. You can just close the valve, close pumps, everything, you can stop the flow. Again you have to start after every reading of hold up. So, therefore, what you have to do? Every time first you have to stop the flow, and maybe you have to divert it to some other area, or you have to stop it completely. Then once after the measurement is done, again you have to start the flow in this particular direction. Again you have to wait for the entire system to attain steady state, and again you have to take measurement. So, therefore, it means that it is a very time taking process, and in industries you very well know that we cannot start and stop the flow in this particular manner so very frequently. So, therefore, it is not used on a large scale, but definitely it is used for calibration of the other techniques. This is definitely the best and the most accurate technique, and this is usually used for calibration, and then maybe the technique which has been calibrated is further used. That technique definitely it has to be an online technique, so that the flow need not be stopped at after each measurement like it is done for the quick closing valve technique. Okay. So, this was one, definitely this is based on a difference in density of the two fluids. This is one. Apart from this, what other physical properties do you anticipate is going to be different for the two phases? Some particular physical property which we can exploit. Maybe some particular fluid will absorb a greater amount of, say, a radiation, maybe gamma rays or X rays or beta rays or something. Some other fluid will absorb a lesser quantity. Naturally, suppose it is water, water will absorb a greater amount of gamma radiation, gas will absorb a lower amount of gamma radiation or any particular radiation. So, therefore, if we know that, well, with a tube full of water, this is the amount which is absorbed. If we know with a tube full of air or empty tube, this is the amount absorbed. Under two phase flow condition, you will get some particular amount of radiation absorbed. So, that if you can link it up in a straightforward manner with the composition, then probably this can be a technique. What is the other thing? Usually we find that the electrical conductivity or the electrical capacitance are different for the two fluids. So, the impedance technique can also be taken. Lot of methods can be used. We find that the velocity of sound is different in the two medium. If we can measure the velocity of sound in only air, only water, two phase flow, and then if we can correlate it to void fraction, this can be used. Large number of radiations can be used. It can be gamma radiation, X rays, beta radiation, neutron emission, microwave radiation, infrared radiation, lot of things can be used. Okay. But it is always not very easy to correlate your difference in physical property with void fraction in a straightforward manner. That we have to keep in mind before we can adopt any technique. Now, the most widely used techniques which are used is, one is definitely volume measurement. The direct method I have already discussed, the quick closing valve method. There are other indirect methods also which are devised in order to see that the system need not be closed down every time after the measurements, but they are also not very successful. There are some indirect volume measurement techniques as well. The next thing is radioactive absorption and scattering. We can measure the amount of radiation which is absorbed, or maybe the dispersed phase it scatters radiation, the amount which it scatters. We can combine the two also in order to know the void fraction as well as the void distribution. That also we can do. Third technique is the impedance technique, which is based on the difference in the impedance of the two phases. It can be either the conductance or conductivity of the two phases or the capacitance of the two phases. So, these are usually the techniques which are used. The most widely used technique is the radioactive absorption and scattering, and then the impedance. Certain other techniques are coming up now and they are being used. We will be discussing them in short at the end of this class. Now, what is this radioactive absorption and scattering techniques? Usually the technique which is used is, it measures the attenuation of a beam of gamma rays during flow. What happens? We have a source. I do not know whether I have a photograph. No, I do not have a photograph. So, what we have? We have a, say suppose we have the channel cross section. Here we have a source of gamma radiation here. This emits gamma rays. Okay. The gamma rays, it penetrates through the wall, flows through the flow passage, and then on the diametrically opposite point there is a detector. So, this particular detector, what happens while it is flowing, it is penetrating the wall, the two phase mixture and the other wall and reaching the detector. In the process, a good amount of it is getting absorbed. So, therefore, the amount which is absorbed, the rest amount will be, some amount may be scattered also, the rest will be transmitted. The amount which is transmitted, that falls on the detector, and we actually measure the amount which is transmitted, and from that we try to get a measure of the void fraction. Now, usually we find that this particular amount which is attenuated, that is a better word compared to absorbed, that takes place by usually the 3 methods which I have written down here. If you see this transparency, the 3 methods or the 3 distinct processes by which they take place, they are the photoelectric effect. Now, in the photoelectric effect, what happens? The gamma photon, it first strikes a particular or rather while it is going through any particular two phase mixture, it gives all its energy to any particular atom, causes electron ejection from the inner orbit. This is the photoelectric effect. The other thing what can happen, it pair production. What is that? It, in this case the photon, it creates a positron electron pair, and in the process it gets absorbed. Then this particular positron, this again produces 2 much lower energy photons. So, this is the pair production, and this occurs usually at high gamma energy, where the secondary photons are much readily absorbed as compared to the incident beam. So, in the first case what happened, it simply strikes an atom, it liberates an electron, gets absorbed in the process. Okay. Pair production, it produces a pair of positron electron. This particular positron, this again produces 2 very low energy photons, which is of a much lower energy as compared to the actual source intensity, and in the process after they are produced, they are also completely absorbed. So, therefore, we can assume that more or less by this pair production also the gamma radiation is more or less completely absorbed by the mixture, and this is usually applicable when we have a very high intensity gamma source or a strong gamma source. The other technique or rather other process by which attenuation takes place is the Compton effect. Now, in this Compton effect, what happens? This gamma photon, it interacts with an atomic electron, okay, and it gives some energy to this atomic electron, and after it gives some energy, it has a reduced energy now. So, it now proceeds at a reduced energy in an altered course. So, since it now has a reduced energy and travels in an altered course, it is expected that it does not reach the transmitter in the diametrically opposite point. Do you get my point? So, therefore, by this particular process also the energy which is scattered, that is more or less related to the initial intensity, and in that particular way we can calculate the amount which is absorbed. Okay. Now, which process is going to be important out of the 3? The photoelectric effect, the pair production, the Compton effect. Out of these we find the relative importance of the attenuating process, that depends on 2 things. What is the gamma photon energy? For example, if the energy is high, pair production is more important. And remember one thing, for Compton effect also, more or less there has to be a good amount of difference between the incident radiation and the scattered radiation. If more or less both of them are of similar energy, then in that case both will go and strike the transmitter. The transmitter will not be able to differentiate between the scattered radiation and the incident radiation. So, therefore, these things have to be kept in mind. So, therefore, the attenuating process, it depends upon the gamma photon energy and also on the attenuating material. If it is metal, it is something; if it is liquid, it is something; if it is gas, it is something else. So, therefore, for our two phase flow we can say, if it is only water, it is something; if it is gas, it is something else; if it is a two phase mixture, then it will be something in between gas and liquid. Now, what it will be, what value it will have, that will not only depend upon the proportion of gas and liquid, it will also depend upon the distribution of the gas and liquid to some extent. Okay? But usually we find that whatever be the attenuating process, we find that the absorption of a beam, it is assumed to be exponential. Usually the absorption of a this collimated word, I do not know whether you have heard it previously. It is just to ensure that the rays of the beam are more or less parallel to one another. Usually when you have a source, what do you have? This particular, suppose here I have drawn this particular source. From this particular source, the rays will come out in all particular direction. Okay. So, therefore, depending upon the path which is travelled, naturally the amount absorbed is going to change. So, therefore, if we have to ensure that more or less equal paths are being traversed, then we have to ensure that the rays are parallel to each other. In order to ensure that, some collimators are used, and therefore, you will find mostly when you are working with radiation, people say a collimated beam. Okay. And remember the other thing also, it is also very important that we have a very small source, so that this beam can be as narrow as possible, such that it can give us an idea regarding the caudal average void fraction. This also has to be remembered. Okay. Otherwise, we are not going to get the caudal average void fraction in this particular way. Now, once we get the caudal average void fraction, naturally our ultimate aim is to get the volume average or the area average. Now, how to transform or how to convert this particular caudal average into cross sectional average? There are two things that we can do. We can place the source at different particular positions along the test section, okay? And at each particular point we can measure the caudal average void fraction. Okay. Now, once we get the caudal average void fraction as a function of position, then we can find out the cross sectional average value by suitable mathematical manipulations. So, the first technique of finding out the cross sectional average void fraction, to find cross sectional average void fraction using radiation absorption techniques. The first one is measure caudal average value as different positions and find cross sectional average by suitable mathematical manipulations. So, this can be one technique. What else? Suitable mathematical technique. Now, remember one thing, if we use this technique, then we cannot measure transient values. This will give you a time average case. Suppose this particular void fraction, it is varying with time. This transient response we cannot get by the technique which I have measured. For transient cases, what you need? You need a large number of beams at the same time which is illuminating this particular cross section, isn't it? This particular cross section at the same time, if we have a large number of very narrow beams, then we can get a transient value. So, therefore, this can also be one. In this particular case, what we do? We can use a multi-beam gamma or X-ray densitometer from a single source. So, from a single source we can use a multi-beam gamma ray densitometer or a multi-beam X-ray densitometer from a single source. Now, this is useful for transient cases, and this is definitely nowadays it is very widely used in nuclear reactor safety work for blow down studies. Very widely it is used in nuclear reactor safety work for blow down studies. What is the other technique that we can use? The other technique, it is usually known as a one shot method. You must be coming across this in your textbooks. This is nothing, this is we have a very, instead of a large number of radiation from one particular source, we have a very broad radiation which is almost the size of the channel. A very broad source we have which is almost the size of the channel, and then we have special collimator arrangements here which adjust for the different path lengths and wall absorption. Is this part clear to all of you? So, what do? In this radiation absorption, we measure the amount which is attenuated. The amount attenuated, that depends, or rather that takes place by 3 techniques as I have written down. It is the photoelectric effect, the pair production, the Compton effect. Now, we find that from all these techniques, whatever be the technique, more or less the absorption of a collimated beam, this can be assumed to be exponential, where I is the initial intensity, I0 is the initial intensity, I is the intensity after absorption, mu is the linear absorption coefficient, z is the axial distance which has been covered. Definitely this mu will depend upon the attenuating material and the source, and therefore, for two-phase flow this mu is going to vary with the composition of the two-phase mixture. Okay. And we find from here we can get the caudal average void fraction. From the caudal average we can get the area average by either of the 3 techniques. The first technique is we can measure it at different particular positions, and then we can obtain the area average by suitable mathematical manipulation. The other thing is we can use multi-beam densitometer, where the multi-beams are generated from one particular single source, and this is particularly useful for transient cases. The other thing is known as a one shot technique, where we have a very broad source which is the same as which is almost of the same dimension as the channel from that particular source, using special collimators, because whenever we use a one particular source there is a tendency of diverging. So, therefore, we have to use special collimators such that each ray is parallel, and we have to also keep in mind that, see, suppose this is the channel. Now, any particular beam which is coming from here and a beam which is coming from here, it has to cross a lower proportion of the channel wall, here it has to go through a higher proportion of the channel wall, a lesser proportion of the flow passage. Okay. So, these things they have to be adjusted. So, therefore, these special collimators, they must be designed such that they adjust for the different path lengths that are being traversed. Here in any case the path length is small, here the path length is larger. So, therefore, it has to adjust for different path lengths which are traversed, and also the wall absorption, the different amounts of wall absorption which takes place. But this one shot technique, this is because this densitometer is quite expensive. So, this one shot technique is quite popular in that particular way. Okay. But whatever be the technique that you are using, see, firstly the initial measurement has to be accurate. Unless the basic caudal average void fraction measurement is not accurate, it is very difficult to get an accurate area average value. So, firstly the initial measurement has to be accurate, and then the subsequent mathematical operations of whatever you are doing, that has to be accurate. Now, for accurate measurements, we know that usually the absorption, it follows a exponential relationship. Okay. So, the best way to get an accurate measurement is in situ calibration. Under the condition of the experiments, you actually fill the tube full of water, you actually perform the radiation absorption experiment, then you empty the tube completely. When it is full of air, there is no water, in that case you see the amount which is absorbed, and after that you start the experiments and to find out that what is the amount absorbed under the actual two-phase flow conditions. Now, we know that the relationship is exponential. As I have shown you in the previous slide, the relationship is exponential. In the transparency that I have shown you, this particular relationship, this is exponential. So, therefore, if this exponential relation has to hold, then definitely your void fraction we should get void fraction from something of this sort, isn't it? From this sort of a relationship, we should be able to get a value of the void fraction. But remember one thing, the relationship, it will definitely depend upon the distribution of the voids, because mu, it is a function, this linear absorption coefficient, it will be a function of the distribution, the amount of voids, and so on and so forth. Okay. So, therefore, by this particular technique we can find it out. Now, remember one thing, suppose we have a hard source. Hard source means the source where the amount which is absorbed is less even in case of water filled tubes. The strong source means high intensity, hard source means a source in which the amount absorbed even when the tube is full of water is also very small. Under that condition what happens? The amounts absorbed, they are very less, isn't it? When the amounts, see, whenever we work with some very small quantities, we can assume linear relationship. This you all of you know. Whatever be the actual relationship, if we are working with small quantities, we can assume the relationship to be linear. Okay. Now, whenever the relationship can be assumed to be linear, the mathematical computations become much more simpler. So, there can be cases where we would prefer to work with hard sources just in order to obtain linearized output, so that getting void fraction from the measured intensity becomes much more straightforward and simple to calculate. This is one particular thing. Okay. Now, what are the difficulties of this particular radiation attenuation techniques? There definitely has to be some difficulties, otherwise this would have been the standard technique. First difficulty, there is no point in discussing it, all of us know it, it is just the difficulty of handling radiations, isn't it? So, handling radiation itself is hazardous, number one difficulty. Number two is that there are some inaccuracies due to normal photon statistical fluctuation. Some errors come up due to, because see, these photons are absorbed and the photons are then emitted, etc., etc. So, good amount of inaccuracy comes out due to normal photon statistical fluctuation. The only way to minimize this particular error is to have long counting times. So, if you have a very long counting time, because this particular error, it is inversely proportional to the number of counts that you take. So, if you have a very long counting time, the number of counts are large, automatically this error gets reduced. The other thing which I was telling, this is influence of void orientation, because we find, no, I do not have it, the influence, we find that the relationships are completely different if we have say the voids are oriented parallel to the radiation and if the voids are oriented perpendicular to the radiation. Usually people have found out that when the liquid and vapor exist in layers parallel to beam, under that condition alpha becomes equal to I minus IL by Ig minus IL. Okay. And when liquid and vapor exist in layers perpendicular to the beam, that means this liquid and vapor, they are oriented in this is vapor, this is liquid, and maybe the radiation is falling this way or maybe the radiation is falling perpendicular. When it falls perpendicular, under that condition alpha equals to ln I by IL by ln Ig by IL. So, we find that even for the void orientation, if they are oriented perpendicular to the beam or parallel to the beam, the expressions are completely different. So, therefore, and also we will find that if it is separated flow and it is dispersed flow, we have different expressions to find out alpha. So, therefore, if we have to find void fraction, void orientation also becomes important. Now, for this particular purpose, for what can we do? The only thing that we can do is we can take up a very hard source, such that, as I was telling, the amount which is absorbed even for the tube full of water is also very less. If that is the case, then more or less all the outputs can be assumed to be linear and we need not have to bother with the orientation of the voids or the flow distribution or the distribution of the voids. What is the other thing? Other thing, as I was mentioning, that the tube wall effect comes on averaging, and this has to be kept in mind. In this particular case, if it is flowing, it has to travel through a large number of tube wall. whereas in this particular case a very small proportion of the tube wall has to is covered. So, therefore, this has to be kept in mind when we are see the problem is if we just see the amount absorbed, no problem. When we want to use it to find out something quantitative, we want to find out alpha, then in that case we have to keep in mind that is, see, suppose in this particular case we get a very low value of I, the measured intensity. It does not necessarily mean that a large amount of liquid is here. It may mean that the large amount of wall had to be traversed, and that is why the amount attenuated was high, the amount transmitted was low. Do you get the point? So, therefore, we have to keep these in mind when we are actually using this particular I to find out alpha, because we are trying to find out something quantitative here. So, therefore, this particular measurement and its interpretation has to be very, very accurate. In this particular case, the I which we get here, the I which we get, both these I's cannot be related by the same equation for alpha. Here we have to make allowance for the fact that the radiation is travelling over a larger distance, whereas in this particular case it is travelling with a smaller distance. So, this effect of tube wall on averaging, because see, from this what we will get a series of I's or a series of alphas, then we will average it and we will get the area average value. So, while we are doing it, we have to keep in mind the I we have got from here, the I we have got from here, both of them cannot be subjected to the same averaging laws, correct. What are the other problems? Time fluctuating effects. This is something very normal for two-phase flow. It is random, it is chaotic, always there are fluctuations, particularly if you take up the slug flow pattern. In the slug flow pattern, what you have, at some point only gas is going. Maybe you have Ig, you will get I almost equal to Ig. At some other point you will get I almost equal to IL. Okay. So, if you just perform an arithmetic average, it is just always you will get the void fraction as 0.5. Okay. So, in this particular case, then average value does not give you the accurate void fraction, the weighted average has to be taken. Please keep in mind this particular thing. The next point which I had written down, the time fluctuating effects, keep this in mind that this is very, very important, particularly considering the time fluctuating characteristics of certain the certain flow parameters, particularly the slug flow. Now, in order to reduce this, what do? We use two different sources which have widely different strength or intensity of the incident radiation. Okay. One may be a very hot source, one may be a very strong source. One emits a radiation of high intensity, the other emits a radiation of much lower intensity. Then we make measurements with both of them, and then we try to find out the average. In this particular case, we find that the average is much more accurate as compared to using a single source. Okay. And what is the other one, the last one, which is very important? Remember one thing, whenever we are trying to find out your alpha, it is very important that we get an accurate value of I, IL, Ig, etc. Now, for getting these, the first thing is the incident radiation. All these relations, if you remember, all these relations come from the basic expression where I have shown. So, therefore, in order to get an accurate value of I, we have to maintain, or rather we have to maintain a constant value of I0, number one. So, the radiation must be of constant intensity. The other thing is, see, we can never work with a ray, we have to have a beam. The beam can be very narrow, but it has to be a beam. Whenever it is a beam, it comprises of a large number of rays. Each ray will have a different intensity. Okay. So, therefore, this I0 of that incident beam, this might vary, and if this varies, it becomes a problem. So, we have to see which particular source gives us a more or less monoenergetic beam of radiation. This is very, very important. The other part is, as I had already mentioned, see, the attenuation takes place by 3 methods. If you remember in the Compton effect, what I said, that it gives some amount of its energy to the atomic electron and then it proceeds with a lower energy. Do you understand? Now, suppose this the basic radiation, it has got a range of intensities, okay, and Compton effect is also taking place. So, from that the scattered radiation, that will have a lower intensity as compared to the incident radiation. Now, if this lower intensity falls within the range of the incident beam, then we cannot differentiate between the scattered beam and the incident beam. Okay. So, therefore, this is also very, very important. The monoenergetic nature of radiation has to be ensured, and this is always not possible. In order to ensure this, usually what we do, usually 2 sources are used mostly for radiation absorption techniques. One is the thulium source, the other is the cesium one. These 2 sources are usually used. Iridium and such other sources are not generally used, because they give us more or less a monoenergetic nature of radiation, and cesium is of course a harder source as compared to your thulium source. Okay. And remember one thing, see, an optimum has to be struck, because for several things, for example, in order to minimize the normal photon statistical fluctuation error, we need a long counting time or we need a very hard source. But again, for minimizing the influence of void orientation, for minimizing effect of tube wall on averaging, we need a very hard source. Hard source means when the intensity absorbed is less, even when the tube is full of water. Okay. So, therefore, what we have to keep in mind? We have to keep in mind that we have to strike a balance between a hard source and a strong source. For some cases a harder source is useful, for some cases a stronger source is useful. Okay. Usually a hard source is preferred in order to get linearized outputs. Okay. If we have to use a strong source, then we have to ensure that the output is linearized, and then by suitable techniques, and then we can use it. Now, apart from radiation attenuation, there are certain other techniques also which are usually used. It can be that maybe the radiation which is incident on a particular two-phase medium, that is scattered. Instead of measuring the amount which is transmitted, we can measure the amount which is scattered. This can be one technique. The other technique can be this particular radiation which is incident on a particular two-phase medium, this it emits or it forces a secondary radiation to come out from the medium. That can also happen. So, we measure the intensity of the secondary radiation which has come out. So, these radiation techniques, they can be radiation attenuation technique, they can be radiation scattering technique, and they can also emit a secondary radiation from the flow passage whose intensity can also be measured. Okay. So, these secondary techniques are, as I have said, that what happens, we can have, instead of a gamma source, we can have a beta source. What it does, this normally this beta rays, they are not very useful. Why? Because they are very easily absorbed by the tube wall. Okay. So, therefore, very less amount passes through the two-phase mixture, but sometimes what happens, these beta sources, they when they fall on the two-phase medium, they emit X-rays from the two-phase medium. Is it clear? And the amount of X-rays which has been emitted, that is measured. This can be one thing. The other thing is, say suppose we have heavy water vapor mixture. Okay. So, this particular heavy water vapor mixture, this can be irradiated by gamma radiation. Now, when it is irradiated by gamma radiation, then what it does? It emits a large number of neutrons from that particular source. From this particular heavy water vapor mixture, it emits a good number of neutrons. And what we can do? We can actually measure the rate of emission of the neutrons in this particular case. This is much more accurate. Why? Because we are directly measuring the amount which has been emitted, instead of measuring the amount which is absorbed and then subtracting two large quantities, is not it? We have to subtract I minus IL by Ig minus IL. So, we are subtracting two large quantities, again number of errors can come up due to that. Do you understand? So, in this particular case what happens? This gamma rays, they are incident on the heavy water vapor mixture, and then from there they emit neutrons. Amount of neutrons emitted will give us a measure of the proportion of heavy water in the flow passage. But this is usually done in nuclear reactors, it is usually expensive. So, under normal circumstances we cannot use this. Okay. The third method, as I have said, instead of measuring the amount of gamma ray which is attenuated, we can measure the amount of gamma ray which is scattered. If the predominant scattering process, or rather if the predominant attenuating process is by Compton effect, a good amount of it will be scattered. The best thing is if we can measure, I think I have got a photograph also. I do not have that particular photograph. Okay. The best thing is, suppose from here we have a gamma source and then good amount of it is absorbed, we have a transmitter here and we also have a transmitter here. We can adjust the source such that the scattered radiation, it is detected by this particular transmitter, the emitted radiation is detected by this particular transmitter, and then from these two measurements we can get a very good idea about the local void fraction here. So, this is one more thing, instead of measuring the amount which is attenuated, we measure the amount which is scattered. Okay, and this is a very good method for finding out the local void fraction in this particular case. And what is the final technique? The neutron scattering method. For this what we have to do? We have to place the medium in a neutron beam, just as I have shown you, and then from here good amount of it is scattered, good amount of it is transmitted. So, the transmitted from here the neutron beams come, and then the amount which is transmitted, it is noted by this detector, the amount which is scattered is noted by this detector, and we can use this. The only requirement of this method is to have a good neutron source here. Okay. So, these were some of the techniques for radiation absorption, which is the most widely used technique for void fraction measurement in the under the present circumstances. Okay. So, remember one thing, radiation absorption techniques, they usually operate on the basis that the amount which is absorbed is a function of the two phase composition. Okay. So, the in situ calibration is the best, where we would like to find out the amount which has been attenuated when the test passage is full of one phase, when the test passage is full of the other phase. Then naturally when there are mixture of two phases, the intensity will lie in between the two. The relationship between void fraction and the measured intensity has to be noted, and only after that we can use it. The only problem is, if the relationship between alpha and the measured intensity is linear, naturally it is easier for us to find out void fraction. If we have to ensure linear relationship, naturally we have to use a hard source where the amount which is attenuated, even for the maximum conditions when the tube is full of water, is also very low. But if we do that, certain errors might also come up. So, we have to keep into mind those particular errors. Other than attenuation, there are certain other radiation techniques also which can be used for void fraction measurement. They are scattering techniques and techniques where this particular radiation, it liberates a consequential radiation from the two phase mixture whose emission can be measured. Why this is a better technique? Because in this case the amount of emission is proportional to the void fraction, and therefore finding out void fraction from the amount emitted is usually easier or usually much more accurate. But we cannot always use it, maybe either the source is expensive or the arrangements are expensive, or maybe there are some hazards in doing this. but overall these techniques are very accurate. They are based on the fact that the amount which any particular substance it attenuates, the amount which it emits, it is a function of the composition of the two phase mixture. So, this particular technique is based on the different amounts of radiation attenuated by the two phases comprising of the two phase mixture. It can be gamma radiation, it can be neutron beam, it can be beta rays, it can be optical rays, it can be any other radiation, as we shall be discussing in our miscellaneous methods. So, thank you very much. We will continue with this discussion in the next class as well.